We currently live in the Stelliferous era, the age of active star formation. But to examine the ultimate fate of matter, we have to advance the cosmological clock far beyond our present day, passing the 100 Google-year mark to reach an almost incomprehensible point in deep time, 10 to the power of 1500 years. By this period, the degenerate era, the thermodynamic reality of the cosmos is entirely alien. Every black hole has evaporated. Standard stellar nucleosynthesis has long since ceased. The universe is a dilute, expanding void, populated exclusively by cold, dead stellar remnants that are cooling toward absolute zero. For our models to work here, we must assume one critical prerequisite: the proton is stable. If protons do not decay, baryonic matter can survive in this frozen state indefinitely, leaving stellar corpses intact across extreme timescales. In 1979, theoretical physicist Freeman Dyson published an analysis of this exact scenario. He wanted to calculate what happens to this surviving, frozen matter when it is given nearly infinite time to exist in a cooling vacuum. The assumption at the time was that a dead star at absolute zero remains completely static. Dyson recognized that even when matter is completely devoid of heat, it is still subject to the laws of quantum mechanics. He theorized pycnonuclear fusion. In active stars, nuclei fuse because thermal energy violently smashes them together. In dead stars, fusion is driven entirely by high density and quantum tunneling, which completely bypasses the need for heat. To accurately map the macroscopic fate of the universe, we first have to correct our mathematical understanding of microscopic quantum tunneling at zero temperature. This cutaway illustration shows the internal structure of a dead carbon-oxygen white dwarf. Objects like this are the physical starting point, the progenitors, for what will eventually become an iron star. Inside this remnant, the density is so extreme that individual carbon nuclei are locked into a rigid crystalline lattice. The physical void separating these nuclei is unimaginably small, measuring a mere 200 femtometers. Without thermal fusion pushing outward, the only force preventing this dead star from immediately collapsing under its own mass is electron degeneracy pressure, a quantum mechanical rule that prevents electrons from occupying the same state. Given 10 to the 1500 years, quantum tunneling allows all of these closely packed carbon atoms to slowly fuse together. The entire mass of the white dwarf eventually transmutes into a solid, heavy sphere of iron-56. This is the iron star. Unlike the stars we observe today, an iron star emits zero heat. It generates no energy and casts no light, rendering it invisible against the dark cosmic background. The iron star exists as a metastable cosmic fossil. It proves that structural evolution continues relentlessly, even long after the entire universe has reached a state of thermodynamic equilibrium. To understand exactly how a dead star manages to fuse carbon into iron, we have to zoom past the macroscopic scale and look directly at that microscopic void separating two individual carbon nuclei. Normally, these nuclei are repelled by the Coulomb barrier. This is a massive electromagnetic force field that prevents positively charged nuclei from touching, acting as a physical wall. This animated diagram illustrates the legacy Zeldovich model. For decades, astrophysicists relied on this simplified parabolic well, which suggests that zero-point vibrations allow particles to occasionally tunnel through the Coulomb barrier at an incredibly slow rate. This legacy model depends on a mathematical shortcut known as the WKB approximation. It treats quantum tunneling simply as a transition from one side of a barrier to the other. The flaw in this approximation is what it ignores. It interrupts the quantum flux at the internal boundary of the nucleus, erasing any calculation of how the wave function behaves once it gets inside. Failing to track this continuous quantum flux creates an incomplete picture of the physics. It artificially depresses the theoretical fusion rate and obscures the true mechanics that govern deep-time astrophysics. A 2023 paper by Sergei Maidanyuk corrects this mathematical oversight by applying the multiple internal reflections, or MIR, method to pycnonuclear fusion. The MIR framework demands strict conservation of quantum flux. It treats the entire spatial region,
both outside and inside the nucleus, as a single continuous environment. This line graph maps the true radial potential for carbon isotopes. Instead of a simple parabola, we see a highly complex shape featuring a towering Coulomb barrier peaking at positive 5.97 mega-electronvolts and a steep, deep internal well dropping to minus 63. In the MIR framework, a particle that tunnels into the nuclear region continues to propagate. The wave reflects and transmits multiple times within this inner boundary, compounding into a built-up summed amplitude. The degenerate electron gas surrounding these atoms does provide some plasma screening, which slightly lowers the overall barrier peak. However, it does not alter the fundamental reflection mechanics happening inside the potential well. By tracking this continuous reflection, the MIR method reveals entirely new behavioral states inside the compound nucleus, states that classical approximations completely miss. These newly discovered behaviors are known as quasi-bound states. They are discrete energy levels where a compound nucleus forms with the maximum theoretical probability. This chart tracks the exact probability of forming a magnesium-24 compound nucleus during a collision between two carbon-12 atoms. Rather than a flat line, we see sharp upward spikes, representing resonance peaks. While basic barrier penetrability rises in a predictable monotonic curve, these distinct peaks indicate a highly specific and exceptionally efficient fusion channel. Because the energy levels of these quasi-bound states are significantly lower than the maximum height of the Coulomb barrier, the newly formed compound system is physically trapped. The barrier prevents it from tunneling back out and decaying. The probability of fusion occurring via these quasi-bound states is orders of magnitude higher than the rates predicted by the old zero-mode calculations. These quasi-bound states provide the physical mechanism required for macroscopic stellar transmutation to proceed until the star reaches its final iron endpoint. Applying these microscopic MIR findings back to the macroscopic scale of a white dwarf gives us a precise timeline for the fate of the universe. On human timescales, the fusion rate dictated by quasi-bound states is effectively zero, but over 10 to the 1500 years, the mathematics make it an absolute certainty. The star undergoes a relentless cascade of transmutations. Carbon fuses into magnesium. That magnesium undergoes further density-induced fusions and alpha decays, forcing the matter to slowly climb the periodic table. This process stops definitively at iron 56. Because iron 56 possesses the highest peak nuclear binding energy per nucleon of any element, it cannot undergo any further exothermic fusion. The resulting iron star is incredibly dense. It has a radius of roughly 2,200 kilometers, smaller than the Earth, but exerts a surface gravity millions of times stronger. The formation of the iron star proves that even in a dark, thermally dead universe, quantum probability relentlessly drives matter towards its maximum state of structural stability. But even the perfect stability of iron 56 is not strictly permanent. To see the actual end of this process, we have to fast forward the cosmological clock to 10 to the power of 10 to the 76 years in the future. Over these extreme timescales, exceedingly rare endothermic pycnonuclear tunneling reactions slowly begin to occur, pushing the matter past the iron limit. These tunneling events gradually reduce the electron fraction of the iron plasma, slowly removing the particles that hold the star up against its own mass. As the electron fraction decreases, the star's effective Chandrasekhar limit, the maximum mass it can structurally support, steadily drops. Eventually, that theoretical limit falls below the actual physical mass of the star. When that threshold is crossed, electron degeneracy pressure fails. Gravity instantly overcomes the star's internal resistance, triggering a catastrophic and immediate structural collapse. The iron star implodes into a neutron star, expelling a massive, violent release of neutrinos and high-energy photons into the void. Because quantum probability never truly reaches absolute zero, the universe's slowest mechanisms will always orchestrate a final, spectacular fireworks display in the dark.